right, welcome to podcast 1.2. This is podcast 1.2. Just saying, hey, I won't be here for very long. After just a second, I will take my face away and you just won't see me anymore. So, on to it. We are talking about the metric system, also called the Système International, which is the French version of it. But, you know, it's getting away from the hoi polloi that is our horrible system of feet and inches and furlongs, and all have their place in history. But, you know, when you have something better come along, you shouldn't just say, I'll keep the old because the old is there. Sometimes you want to go ahead and change units. So the SI system, as shown by the picture here, is about kilograms and meters and seconds and a bunch of other stuff that we don't really talk about, candelas and Kelvin, but for the purposes of this, we'll be concentrating on the things that we will see in lab, the things that we'll use to collect data. In order to have a unit, you need a standard that doesn't change. So long time ago, the king's foot in England, the king's foot was the basis of measurement. So if you got a new king, of course he came with a different size foot. And so when you did, you got a new measuring tool or a new ruler. So it's the idea of king being ruler. Anyway, that changes around and that makes it really hard. Same thing for shoe size. Your shoe size is 8.5. 8.5 what? Is it inches, feet? It's just that happy little meter that they have on the little scale at the store. We need a unit that doesn't change. So a meter is based on the speed of light, and a meter is about 39 inches. So it's pretty much the same as a yard, a little bit longer than a yard. This is the official definition of it. We don't really care what the official one is, but it's based on how fast light travels in a vacuum. So light traveling through space or light traveling through anything except air, really, goes this certain speed. And so light goes 300 million meters every second. We can measure that if we have a long enough tunnel. And so we came up with this idea of, let's use light, because the speed of light is constant in the universe. Right? So that's how we came up with the basis of the meter. And we use that for length. And if you know meters, then you can know centimeters. Then volume, how much area, how much space something takes up. You would say quarts, gallons, pints, teaspoons, tablespoons, right? Well, for us, we just need to know that a liter, and you know what a 2-liter bottle is, but a liter is about the same thing as a quart, right? So there are 3.8 liters in 1 gallon, 3.8 in 1 gallon. But we define a liter as a box that is exactly 10 centimeters by 10 centimeters by 10 centimeters. So if you had a ruler and some paper and some wood or whatever, and you could build that box, then you would know that it's definitely, that's definitely 1 liter. Since the centimeter is based on the meter, is based on the speed of light, then voila, the liter is also based on the speed of light. And you know that 10 times 10 times 10 is 1,000. So 1 liter is equal to 1,000 cubic centimeters. All right. The last one we worry about, we have a couple other ones, but the last one we worry about the most in lab is mass. How much matter something has. This is not the same as weight. Weight is a function of gravity. So the more gravity there is, the more you weigh. So for instance, if you are on the moon, there's less gravity. You would weigh less. If you're on top of a high mountain in the world, in our world on Earth, you would weigh less. If you were below sea level, like in Death Valley per se, then you would actually weigh more. The closer you get to the center of the Earth, the more gravity there is. And so weight changes. So we don't want to talk about weight, but we do want to talk about mass. And we use the idea of a gram or kilogram. A kilogram is just 1,000 grams, and a kilogram is about 2.2 pounds. It's actually 179 something, and they rounded, but you should know that a kilogram is about 2.2 pounds. So it's based on a liter of water at 4 degrees. 4 degrees is important only because that's when water is its most dense. So go to the bottom of a lake. Your refrigerator is about 4 degrees Celsius. And if you had water that was 4 degrees and you measured a box that was 10 by 10 by 10 centimeters and you filled it full of water, then you would know that that was exactly 1 liter. I mean, 1 liter of water, so it would be exactly 1 kilogram. And so that's where we came up with that. Now, temperature, you guys know Fahrenheit. Most of y'all know Celsius. I'm not going to have y'all convert this in class, but just realize every 1 degree Celsius is equal to 1.8 Fahrenheit. So if you ever had to do a rough calculation, and you can see here on the screen, if I said, oh, it's 30 degrees Celsius outside. Oh, okay, well, let's see. What's that? 30 degrees Celsius, every 30 degrees is 1.8 Fahrenheit, so that's why I did that math. And then you know that 0 Celsius starts out at the same place as 32 Fahrenheit, so we can add them together and get 86. A couple little points along the way y'all need to know. Number 1, 0 degrees Celsius, water freezes. You knew that, right? 100 degrees Celsius, that's when water boils. 37 degrees Celsius is your body temperature, so like 98.6. And room temperature is usually, in Bob Jones High School, is usually around 22 degrees. That's about the room temperature. So it just gives you a rough estimate of when you see a temperature, how warm is it. There is one other temperature system we use sometimes, and it's the Kelvin system. All right, the Kelvin system is based on the idea we need a temperature system that starts at 0. Not negative numbers, starts with 0. Because we know at 0 Kelvin that no matter is moving. It's not vibrating, it's not racing around, nothing. So Lord Kelvin came up with the idea of absolute 0. And you can see there how to find absolute 0, how to find Kelvin given Celsius. You just add 273. Right? You guys are going to need to know prefixes. So this is a list of lots and lots of prefixes. And let's just say that you guys are going to need to know, on the big side, let's go from tera. So 10 to the 12th. Tera means 10 to the 12th. So a teragram is 10 to the 12th grams. A terameter would be 10 to the 12th meters. A terabyte, some of y'all might have a computer with a terabyte of memory in it, or a terabyte hard drive. Then that's a 10 to the 12th. A giga, that's pretty standard. That has 10 to the 9th. So you guys can do the math and see that a terabyte of memory has 1,000 times as much as a gigabyte. When I was young, we measured memory in kilobytes and kilohertz and stuff like that. So on the other side, on the right-hand side, you guys need to be concerned with all the way down to nano. All right, now it goes way past that, but a nanogram is oftentimes used when you're talking about masses of individual atoms. Right, so you guys are going to need to know these prefixes. I'll show you a trick in class in case you're not a good memorizer of facts like this. There's a visual method. It's called the metric staircase, and I'll show you all that in class.